Oh. Okay, so let's start in 4 minutes. No, let's say 5 minutes, right? At 10:05. Cool. Hello, Tune. Hey, Yona. Hey, Chris. Sup? Chris, you're so fun. Hey, Sarah. So I got your email, Sarah, and we're going to do some pretty cool conservation of momentum problems. Okay? So get pumped for that. So we got 2 more minutes. Hey, Mr. Halpern. Just making some tea, Alex. It's that kind of morning. Look at that color. Delicious. It smells so good. I'm really sad we're not together. So you could taste this. Okay, so today we're going to be going over. Hey, tomorrow, what's going on? What's going on, kiddo? Pound it. Okay, so I guess this is half review for the AP Physics 1 exam, and just half like stuff you should know. Like this is stuff we learned like 2 or 3 months ago, and actually not more than like 4 months ago probably. And I just think it's like really useful. Okay, so first of all, like we want to talk about momentum. Okay, right? How do we define it? There's a lot of different ways to define it. I like to define it as like a quantity that measures how hard it would be to stop an object. Right? So if something's moving towards you, the faster it is, obviously, the harder it would be to stop, and also the more massive it is, the harder it would be to stop. Right? So we have this really simple formula where momentum is equal to mass times velocity. It's really important that you recognize that those are like vector quantities, right? And no matter what you do, either with a positive or negative sign, or with just your just like with your words, you need to be able to specify the direction of the momentum, and it's going to be identical to the direction of the velocity. Okay? All right. Why do we even care about momentum? Because in the grand scheme of things, right? Okay, and then there's another quantity called impulse. Okay? And it's equal to the change in momentum. But it's also equal to its own letter. I mean, we abbreviate it with the letter J, right? And it's simply equal to the force times the time interval during which that force was active on an object to change its momentum. Because you want to say like, well, how do I change an object's momentum? I can either change its mass, which we're not really doing in the context of AP Physics 1, right? Well, how's that even possible? Don't worry about it. Don't worry about it. Okay, and or you change its velocity, right? And how do I change an object's velocity? I accelerate it. How do I accelerate it? I exert a net force on the object, right? So whatever force I exert on the object for amount of time is going to give me a change in momentum. And you'll notice that both of these quantities, right? If you work it out, simplify, the units would be in kilogram meter per second or a Newton second, right? And those are the units of momentum. Why do I even care about impulse? That's like a really great question because it's not super necessary. It's the same thing as calling change of position displacement, right? Certain quantities we use so much, we just give them their own name, right? So anytime I talk about delta x or displacement, I could always just say change in position, change in position, change in position. It gets kind of old, so we just call it displacement, right? Same thing. There are a lot of problems where you're going to be working a lot with the change in momentum a lot, so we just call it impulse. We just give it its own name. Force. So what Sarah says, how do I get impulse? If I have a force, right? If I attach a force meter to an object, right, and I can measure the force acting on the object the whole time, right? For example, like for me, right, that force versus time graph looks like this. Why do I know there's no net force on me? Well, because am I accelerating right now? I don't think so. My center of mass is just right here, and it's just staying, right? So it doesn't really matter. But let's say for an arbitrary object, like the force versus time graph looks like that, right? So initially there's zero force, and then eventually, like you keep pushing it harder and harder and harder, right? Sarah, it would be the area that would give the impulse, all right? The slope would have units of newtons per second. The area has unit of Newton seconds, okay? And that's exactly what Itamar just put in the chat, right? Yeah, if you want to know about what the units are and what the things are, like this, the units of whatever the slope is the y-axis units divided by the x-axis units, and the unit of what the area is the y-axis units times the x-axis units. It's not always going to give you a hint as to like what it is, right? Like for instance, like I know this area, its units are in Newton seconds. So is the area the momentum or is it the impulse, right? Because there's two things that are measured with Newton seconds. And a lot of times you'll get that, like the area will be measured in maybe meters, right? So, well, what does that area represent? Is it length, width, height, displacement, right? I don't know, right? Usually the area is always going to correspond with a change, right? Oh yeah, and another one, like, so if I do, like for example, like if I have a force versus distance graph, and I take the area of it, the units will be Newton meters. So those are joules. So what is that? Is that energy? Is that potential energy? Is that kinetic energy? Is that work? Is that torque? Right? Torque is in Newton meters, but there's a hidden radian in there. Always think about, the way I like to think about it that way is the area always represents a kind of change, right? So this is measured in Newton seconds, and it's a change in that. So, oh, it's the change in momentum, it's impulse. Force versus distance, right? Area, it's the units are joules, and it's a change. Oh, it's change in energy. It's work, right? Because that's, yeah. Okay, so, and that's why the velocity versus time, the area of that is a change. It's the displacement. It's the change in position, right? So area always represents a change, okay? Remember that. So anyways, so we have this, and that's impulse, and I get impulse from this graph if you're ever going to be asked about a graph, okay? But more importantly, I want to talk about like why we even like to talk about these, okay? And the big kahuna is there's a law of conservation of momentum, right? Which says for a closed system, right, the sum of all my momenta is a constant value, right? For my calculus kiddos, it's just d, the sum of p dt equals 0, right? That's another way of writing that. Why is that true, right? So if you remember, if I have a closed system, right, that means if it's a two-object closed system, that means the only forces that are present are those between the two objects, right? So this is 1 and 2. That means if one exerts a force on 2, and I know that some textbooks do this backwards, right? You would interpret this as the force 2 exerts on 1. I always go left to right, right? So if that's a little confusing, I'm sorry, all right? So if 1 exerts a force on 2, that means 2 has to exert a force on 1. That's Newton's third law. And those are the only 2 forces in the system. If there was a third force and let's say like 3 on 2, right? Well, that means there's an object 3, and due to Newton's third law, 2 would also exert a force on 3. But this system wouldn't be closed. This system is closed, right? It's only when I account for all the if everything that's exerting a force is in the system, then it's closed. That's how I define a closed system, right? And using this, right, you can really see that if I add all the impulses together, right, the net impulse equals 0. Why do I know the net impulse equals 0? Because the impulse due to this force and the impulse due to this force totally cancel out. Assuming the time is the same, and of course they're the same. When objects collide and like one object exerts a force on the other object, that force is only exerted like while they're in contact or when the force is active, right? And as soon as one force becomes inactive, the other force becomes inactive due to Newton's third law as well, right? So these forces, right? So this impulse right here, I'll call this impulse A, equals F21 and then like a time interval A, right? And then impulse B is just F12 times time interval B. What I'm saying is that the time interval of B is equal to the time interval of A, right? Because these two forces exist at the same time. When one exists, the other exists. That's third law, right? And one doesn't exist, the other doesn't exist. Because if this one didn't exist while this existed, that would violate Newton's third law. Hey, Ayanava. Hey, Jared. Right? So what does that say? If the times are equal, but the forces are in completely opposite directions, then if I add those two together, they cancel, right? And likewise, if I add those two impulses together, they cancel. So the total impulse is 0. If the total impulse is 0, that means the total momentum has to be a constant value because the change in total momentum is 0. So that's one mathematical way to write conservation of momentum. The other way with which we're much more familiar, the other way with which we are more familiar is just like P1 plus P2, right, plus equals P1 prime plus P2 prime, right? So it means the sum of all momenta is equal to the sum of all momenta at a later time, okay? That's what the primes are used for. Some people, I mean, the other way to write that, it's clunky, is this, like P1I plus P2 initial equals P1 final plus P2 final, right? The reason why I don't like this is because it really limits you into talking about two times in particular, right? If you want to look at, for example, like a third point in time, like maybe like 2 seconds after the collision, rather than just like right after the collision and right before the collision, maybe you want to know like what happens like 2 seconds after the collision, then you could use like a double prime reference frame, right, with respect to time. So that's why I like using primes, and also it cleans up your subscripts. So you don't have to use like 2 subscripts. Where it falls short using primes is like when you have to square things or cube things. I know, okay, but you got to make compromises somewhere. All right. With any conservation, right, I don't want you to automatically think of this equation, right? This is a pretty boring equation. Like, for example, like for the two-body problem, it basically turns into this. And between M1, M2, V1, V2, V1 prime, V2 prime, you're usually going to be given like 5 of those 6 variables, and you just solve for the 6th one. Boring, all right? What you really have to look at in any conservation of problem, whether it's momentum or energy, right? Some important key conceptual takeaways is that if I give you a statement that says A plus B is constant, that tells you so much information, right? Like, for example, that will tell you when A is big, B is small, right? Because it's the sum is constant, right? So if you're looking for like where A is the smallest, for example, and you're not really given enough information about A, you'll just look for where B is the biggest, right? An example of that is like a ramp and a ball going down the ramp and back and forth, and I say, well, where is it the fastest? Right? Well, there's a situation where the gravitational potential energy plus the kinetic energy is constant, right? And to look at where kinetic energy is the largest, I'll have to look for where gravitational energy is the smallest, and that happens to be right there. And that's why I'm fastest there, right? So conservation has, I think, we covered a lot of things about conservation, right? First of all, we derived why conservation of momentum is even true in the first place using impulse and Newton's third law. But then we went over like two applications of conservation. One, you can write primed equations like this, where you can set one sum equal to the sum of it at a later time, right? But more importantly, I think it's just as important, right? Just as important, it allows you to look at relative minima and maxima, right? Especially if it's just the sum of two things that's conserved. All right. Moving on to more juicy stuff, I want to go over probably a problem that combines like moment collisions and so let's use the basic conservation of momentum equation for a two-body problem. Oh, what the heck? Sorry. I did not get a lot of sleep, and apparently my tea has not yet kicked in. Right, this is a really basic equation that says, hey, for this closed two-body system, momentum is conserved, right? In addition to that, I can like expand it, and because I know momentum is just m times v, right? This becomes m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime. Whoa, okay, why? There's a good reason why I'm not priming the m's. We're not dealing with problems where mass ever changes, right? And there are a lot of different ways you can go with this. If you set both objects to be initially at rest, right? So here's example one, right? Example one, right? So both objects initially at rest. What does that guarantee, right? That just means 0 equals m1 v1 prime plus m2 v2 prime. That guarantees that v1 prime and v2 prime are in opposite directions, because the sum has to be 0, so one needs to be positive, one needs to be negative. They're going to go in opposite directions. That's basically how we justify or explain why recoil happens, like why when I throw something or launch something, I go backwards, because initially the total momentum was 0. Just know, recoil isn't always when both objects start with 0, right? Recoil still happens, like if I'm moving forward and I throw something, there's still recoil. I might not go backwards, but so there's three options that can happen. If I'm moving this way, right, and I'm moving this way and I throw something, right after I throw it, there's two options, right? I could throw it so hard I actually do go backwards. I could throw it perfectly so I like stop, and I can throw it and I'll just slow down a little bit, right? Either way, the impulse that I experience is going to be pointing this way, and my forward momentum will decrease, right? It'll go in the opposite direction. All right, so example 2, right, that I think is special is if they're both moving. I don't care if they're moving this way, or this way, right? But they stick together. This is what's known as a perfectly inelastic collision. All that means is v1 prime equals v2 prime. All right? So, and then you can solve for the problem there. You'll notice, though, that if they're equal, that you can factor out came back to me. Cool. All right. You can factor out this part, right? And the right side of your equation becomes, oh, I meant to circle this part, by the way. It'll become m1 plus m2 times v prime, right? Where v prime equals like whichever one of those. And you're essentially treating the right side of the equation, like the later point in time, just to be one object. There's only one object there, and it has this combined mass, and it's traveling at this speed. So the math is kind of identical. It's just like how you choose to interpret the result. You can either picture them, like if you actually have like m1 v prime plus m2 v prime, you're literally seeing this as like two objects moving at the same speed. Or you could just say parentheses m1 plus m2 times v prime. And then you're actually just imagining them and modeling them as one combined object moving at v prime, but it's identical and it's the same. All right. The third case, I mean, there are like a lot of different ways you can do this, and I'm not really interested in the other ones. I want to jump straight ahead to an example problem, right? Probably the most significant type of example problem that you can be asked and that I like to ask, right? Some of my students will find this familiar, okay? These types of problems, right? There's an object and a small projectile is launched with some speed v, okay? Maybe I'll call it v naught, okay? So this is the initial velocity, right? So remember, like v initial is basically the same as v naught, right? Why do I call it v naught? Because the 0, which is the naught, stands for time equals 0. So it's like the velocity at time equals 0, which is another way of saying initial velocity, right? Okay, and there are, I want to say, let's say there are 4 options. Okay, most problems will only give you like up to 3 options, but there's actually like 4 things that I can kind of think about that could happen here. No, let's go over 3, and then I'll give you 2 bonus options. All right. So the first is, this is what's known as ballistics. Okay, it's when I like launch objects into each other, pow, right? There's 3 options, so they collide. So option 1, after they collide, is the bullet sticks, all right? It's like stuck in there, right? Option 2, the bullet bounces backwards, right? It's like a really bouncy bullet, okay? Pew! Right? So it bounces back, all right? And the third is maybe the material was so weak that the bullet goes through, okay? So these are like the 3 scenarios that you can go in, all right? And every question you'll see related to this is basically going to be asking the same thing. In which case is this the big target, right? The target. In which case is the target speed the largest, okay? Oh, excuse me. Right? When is it going to be the fastest after the collision, all right? So I really like these types of problems. Oh, whoops. Pew! Okay. And here we go. So this is a basic conservation momentum problem, right? So as soon as you see this, you see collision. Boom. You should immediately be thinking about momentum, right? And you're talking about the speed of 2 different objects, right? I don't really care about what their masses are. And so my first instinct is to always do this. P1 plus P2 equals P1 prime plus P2 prime. And what am I really looking at? If I call, let's call this 2, right? And this 1. All right, so what I'm really looking for is V2 prime, right? So I'm looking at what things make P2 bigger. Well, what makes P2 big? When is P2 big? Or when is P2 prime big? Right. What happens if A plus B is a constant value? When is B really big? My chat. When A is small. Exactly. So I want to look at what has the smallest value of P1 prime, right? Yeah. So the smallest one is actually 2, right? Because guess what? I'm counting negative values now, right? So P1 prime in case 2 is the only case where P1 prime is actually negative. So that makes P2 prime super big. So this is clearly, the fastest, right? Yay! Yay, it's the fastest. But what if I want to rank the other two, right? Because from now on, it's now a battle for third, right? Why do I say it's a battle for third? Because there have been numerous psychological studies on Olympians that follow the mental health of people who compete in the Olympics. And overwhelmingly, bronze medalists are much more at peace and like just, mentally cool than people who win the silver medal. Because, and you can imagine like the reasons why, right? Like the silver medalists would feel that they were like so much closer and like have a lot more regret, where bronze medalists are like, yeah, I'm just happy to be on the podium. Top 3 in the world, not bad, you know. But the second place guy must be like, oh, I was so close to gold. Anyways, so I like to like flip the paradigm. It's a battle for third because you're going to be happier long term with your life if you get third. So which one is actually going to be the slowest between case 1 and case 3? Well, if we go back to our old strategy and say, hey, which one has the bigger or smaller P1 prime? It's really hard to tell. It's really hard to tell, right? Like you might want to say like, oh, this one is obviously faster, and that could be true. Yeah, it is, right? Obviously, this one is fastest because it actually goes through. Okay. And for that reason alone, this is third, right? And this is second. Chris, we don't care about mass because what we're really doing is we're comparing P2 prime between these 3 cases. And P2 prime equals M2V prime, right? So whichever of the 3 cases has the bigger P2 prime has the bigger V2 prime because all 3 cases have the identical M2. If you want a more rigorous proof of like why this speed is actually faster than like their combined speed, I'll leave that as a thought exercise. There are ways you could do it using center of mass, like velocity of the center of mass, right? You could say because it's a closed system, like for example, right? This is a good chance to get into center of mass. In any closed system, the velocity of the center of mass is constant, right? So that means in this situation, the center of mass is probably here, and it's moving slow. It's moving slower than that, right? And this velocity of the center of mass of this system is the same as these three systems, right? Because this system turns into these three, and since it's a closed system, the velocity of the center of mass is always going to be the same, all right? So in that case, I know that these two scenarios have the same velocity of the center of mass. The velocity of the center of mass here is simply just that, right? This is that. And the velocity of the center of mass here, this ball has a velocity that's slower than the velocity of the center of mass, and this bullet has a velocity that's faster than the velocity of the center of mass, because the center of mass is always between them, and it's like traveling this way, right? Like I'll make the center of mass purple. It's just gonna do like this, right? Right. So obviously, like the bullet is a faster velocity of center of mass, but this bullet has a velocity equal to the velocity of center of mass because they're traveling together. Therefore, this bullet is faster than that bullet. That's another way of looking at it. All right. We're almost there. Wow, let's talk about like how we can apply these types of problems, right? There's one other way to do this problem, and it's to look at, if I'm looking at speed of the ball, right? You can also look at the bullet and look at its impulse, right? Because the impulse the bullet experiences is equal, well, the magnitude, right, is equal to the magnitude the impulse of the target experiences, right? And the more impulse this experiences, the faster it'll go, right? So in which of all these cases, does the bullet have the most impulse? Obviously, the bullet has the most impulse there. It's actually changing direction. So it has like the most impulse there, right? What about this bullet? It has slowed down less than that one, so its impulse was the smallest. So that makes this the slowest as well. All right. Why do their impulses match up? Like, why is the impulse of the bullet equal to the impulse of the target? Because conservation of momentum, right? The total impulse must be 0. Right? So I wrote this in absolute value, but the real formula would be like J1 equals negative J2. Right? Cool. That's the other way to look at it. It's harder because you're going to have to assume all 3 collisions happen for the exact same time interval, stuff like that. But not really. Okay, so where do I see this applied? A lot of times the problems won't be so direct in asking like which one's the fastest. They'll have a scenario like, oh, this bullet goes into this thing, and like, which bullet gives it the greatest theta? That's just asking for which one is fastest here, right? Because obviously, the faster this is, the more kinetic energy it has, and the more kinetic energy it has at the bottom, right, the higher it can go and turn all that into more potential energy, right? So asking for what has the greater theta here is the exact same as asking what has the greatest speed at the bottom, right? The other way to do that is to put it at a ramp, right? Bullet. Well, which bullet makes the ramp go higher? It's just which bullet. Those are 2 ways of masking the question, which bullet makes the block go faster, right? When they're asking like how high does it go, or the bigger angle, right? Is there another example of that problem I can think of? Yeah, like which bullet will make it the spring compress the most? You know, it's same thing, you think. Okay. Oh, but the spiciest version, I think, is like a door. Okay. Right? So here's my door, and I throw a ball at the door, right? Same thing, right? Which ball is going to make the door rotate the fastest? That's a problem like going into angular momentum. And you can think about it the same way, right? Because ultimately, like, conservation of angular momentum is the same. So I'm talking about, hey, so if the angular momentum of the door plus the angular momentum of the ball is always constant, when is the angular momentum of the door the largest? When the angular momentum of the ball is most negative or smallest, right? And angular momentum has two formulas, right? One is I omega, and the other is R cross P. So for the ball, I will use R cross P because it actually has like a distinct linear momentum, right, which is P. And of course, when the ball changes direction, it has the greatest change in P, right? It actually has a negative P right there, and it'll make the door L really large because it makes the L of the ball really small, right? Chris, about rotational mechanics, I don't. Okay, so well, your exam's tomorrow, right? Yeah, they all. I mean, everything is identical except what happens immediately after the collision, right? That's the whole shtick of these problems. Dimon. Did this review make sense? Is this cool? I hope it was helpful. Okay. No, Yona. The slower, not just slower, right? No, I'm looking at the bullet after the collision. Because in every case, like, the initial conditions are the same. Is that what you meant to say? Like, the slower it is after it hits, the faster the block will go? Because remember, before the collision, they're all the same, right? Yeah, and remember, it's not just slower. It's the real faster case is when, like, the final momentum is negative, because that would make the final momentum of the other thing really big, right? So it's not just slower. I would change it to most to negative. Do you know what I mean? Like, or if I'm looking at the thing that's going backwards, when is that the fastest one? When the thing that's going forwards is going forwards the most, right? Yeah. Okay. Unfortunately, I don't think we have time and to go over rotational mechanics, but I think, like, let me look at the channel, Chris. I think we did go, yeah. So on May 6th, which was a week ago, at night, right? We did a rotational review for the AP Physics 1 exam, right? And I know it didn't cover everything, but I think it covered a fair bit. And we did cover it a little bit also in problem 1 from the time to practice. Okay. So the perfectly elastic is the fastest. Yeah. Yeah. Okay. All right. That's it, guys. Have a great day. And for those of you taking the exam tomorrow, good luck. For those of you not, way to stick it to the College Board. And what time is it tomorrow, the exam? Can someone tell me? What time is it? Four. Okay. I don't really want to have class tomorrow then, right? I mean, I feel, maybe we will have class. Yeah, I don't know. I'll think about it. But have a great day. All right, see you guys. Good luck tomorrow if I don't see you before then, okay? Bye.